Good morning, calculus students. So Mr. Chen again. So welcome back. So today I would like to talk about that 10.5 from the Rokawski Calculus BC textbook, ratios tests. So once again, it's about the infinite series. So there's so many tests in this unit here. So one of those is considered the ratio test. So the ratio test, so this one shows three different type of condition here. So the series a sub n converges absolutely if the limit of a sub n plus 1 over a sub n with the absolute value, it's less than 1. Okay, so anytime they see the limit of absolute value of a sub n plus 1 over a sub n, it's less than 1. So that means the series, so it's considered absolutely converging. And then what about for condition number 2? So the series diverges if the limit of absolute value of a sub n plus 1 over a sub n, it's greater than 1. If you find out any number is greater than 1, 1.5, 2, 10, infinity, whatever that is, so you see that the absolute limit, it's greater than 1. So that means the series is considered divergent. And then using the ratio test, we find out that the limit of a sub n plus 1 over a sub n with the absolute value equals 1. So this one would be considered inconclusive. Not enough evidence to state that whether it's convergent or divergent for the series. Okay, so now let's try to do some example here. So test the series negative 1 to the power of n to the power of 3 over 3 to the power of n using the ratio test. So one thing that we need to identify in here is that a sub n. So what we found, it's n to the power of 3 over 3 to the power of n. And by the way, it's an alternating series. It is. But we just want to take out that a sub n. And also we want to set up that a sub n plus 1, the next term, which is considered n plus 1 quantity to the power of 3 all over 3 to the power of n plus 1. And then by using the definition of the ratio test, so we take the limit as n approaches infinity. So this one is saying that a sub n plus 1, so we put that n plus 1 to the power of 3 all over 3 to the power of n plus 1. So instead of dividing a sub n, we just want to multiply the reciprocals of a sub n. So then that would be 3 to the power of n over n to the power of 3. Okay, so let's put it in this way. And now you might be wondering things that we can cross cancel. Yes, so there are certain things that we can cross cancel here. So 3 to the power of n, 3 to the power of n, well, let's just rewrite it. So limit n goes to infinity. So what we found, it's n plus 1 to the power of 3 all over 3 times 3 to the power of n. So using the properties of exponent, so times 3 to the power of n over n to the power of 3. So you may notice that 3 to the power of n, 3 to the power of n got cancelled. So what's left here, it's just the limit n goes to infinity of, well, 1/3. We can always put it out, 1/3, because that's the coefficient. And then on top of this, we do have n plus 1 quantity to the power of 3 all over the denominator n to the power of 3. So you might be wondering, try to expand it out. So this one, we can use the L'Hopital's rule, definitely. But eventually, the limit of this quantity, it's going to be 1. 1 times 1/3, so that's going to be 1/3. Okay, so going back to the definition, 1/3, it's actually less than 1. Okay, so therefore, the limit, it's 1/3, it's less than 1. So therefore, the series converges absolutely. So negative 1 to the power of n cubed over 3 to the power of n, converges absolutely. Well, again, back to the alternating series, the absolute convergence theorem. It's saying that if the series converges absolutely, that means the series itself also converges. Okay, so now here's another example using the ratio test to verify that whether it's considered convergent absolutely, or it's divergent, or it's inconclusive. Okay, so started with a sub n equals n to the power of n over n factorial. And then a sub n plus 1, so then that'll be n plus 1 to the power of n plus 1. And then all over n plus 1 quantity factorial. Okay, so one thing that you might be noticing here, so this one with the factorial, so factorial is like 5 factorial is like 5 times 4 times 3 times 2 times 1 for those people just need some refresh with the factorial. And now let's put this all together. So limit as n approaches infinity, so n plus 1, quantity to the power of n plus 1 over n plus 1 factorial, divided by a sub n, so multiply the reciprocals of a sub n, so n factorial over n to the power of n with the absolute value. So again, rewrite it, so try to simplify it a little bit. So what we found here, it's n plus 1 to the power of n, and then times n plus 1. Okay, so I just want to split that the power, so using the properties of exponent. And this one is just like n plus 1 factorial, so it's written as n plus 1 times, the next term would be n plus 1 minus 1 quantity factorial, which is n factorial. Okay, so just rewrite it. And then times n factorial over n to the power of n. Okay, so this one might be a little bit tough. Okay, so now things that we can cross cancel here. N factorial got canceled, n factorial got canceled, n plus 1 got reduced. And what's left here? It's just n plus 1 to the power of n over n to the power of n with the absolute value. So now got to be very careful with this, so I need a little bit more space. Okay, so let me just put it down here. So this one can be written as limit n goes to infinity, n plus 1 over n to the power of n with the absolute value. So going back to what we did with the L'Hopital's rule, so this one we can always set that y equals n plus 1 over n. And then we can take the natural log on both sides to bring down the power. So this one you got to be very careful. So let's say y equals n plus 1 to the power of n over n to the power of n. And then take the natural log on both sides. So you can bring down the power. Well, we do know that this part right here, if you plug in n goes to infinity. So this one here, the limit, it's going to be 1. Okay, so it's like infinity times L natural log of 1. Well, natural log of 1, which is what? 0. Okay, so infinity times 0, then that'd be 0. And then you take the base e on both sides, so you see that the limit of this series, well, the ratios of the series, then that'll be 1. So again, back to what we talked about before, if that's 1, so this one is considered inconclusive. So inconclusive, that means we need to do something else. Okay, so try to use the ratio test. So this one, it doesn't work. Okay, so we need to verify that with the other technique. Okay, n factorial. So this one we'll save that for the root test later on. Okay, so the ratio test, you'll see that it's considered 1. It doesn't work. Okay, so now let's try to verify the other one. So example 3. Okay, let me get some space down here. So the ratio test and the root test, they're kind of similar. So we'll get to that for the next part of the video. But now let's use the ratio test to verify that the alternating series. Okay, so this one we just did that. So this one, it's considered 1, which is inconclusive. And now what about for this one here? So started off with a sub n equals 1 over n to the power of 1/2 over n plus 1, and then a sub n plus 1, then that will be considered n plus 1 quantity to the power of 1/2 over n plus 1. So using the ratio test, so the limit, n goes to infinity, absolute value of n plus 1 to the power of 1/2 over n plus 1. divided by a sub n. So multiplied by the reciprocal, n plus 1. This one, a sub n plus 1. I think I did something wrong here. This one's supposed to be n plus 1 plus 1. So that would be n plus 2. Okay, so this one is n plus 2. So n plus 1 over n to the power of 1 half. So you might be wondering things that we can simplify, cross cancel, things that we can reduce here. So it looks like nothing we can reduce. Okay, so if you just compare the power, n plus 1 over n plus 2. So basically, if you find the limit of that, we can regroup them. Regroup. So we do have n plus 1 over n plus 2 times n plus 1 over n to the power of 1 half. So using the limit property here, so this one would be 1, this one would be 1, so 1 times 1, it's also 1. Okay? So try to use the limit property. So this one's, you can just split it, n plus 1 over n plus 2 using the L'Hopital's rule, times the limit of n goes to infinity, n plus 1 over n, and then square root. So try to use that, the L'Hopital's rule, this part right here, using the limit approach, and then you'll see that the limit would be 1 times 1, which is 1. So therefore the limit is showing that it's 1, so the series is considered inconclusive. So we don't know whether that's divergent or convergent. So that means we need to use the other approach to find out whether the series converges or not. So definitely we're not sure about whether that's absolutely convergent. Okay, so using the alternating series. So you try to verify that by using the alternating series. So this one, if you take the limit, n goes to infinity, n to the power 1 half over n plus 1. So it's infinity over infinity using the L'Hopital's rule. So we'll see that this one here is 1 half, n to the power of negative 1 half. So this one is going to be considered 0. And also we want to verify that by finding out that a sub n plus 1. Okay, so using that a sub n plus 1 to compare that with a sub n. So going back to what we did for the previous video, alternating series test. So the limit as n goes to infinity, it is 0, so it satisfied one of the conditions. And then we want to find out a sub n plus 1. So for a sub n plus 1, this one is considered root n plus 1 over n plus 2. So if that's root n plus 1 divided by n plus 2, well, let's find out, is that going to be considered smaller comparing with that a sub n? So let's plug in n equals 1. So that's n equals 1, so we do have root 2 over 3. And then back to that a sub n itself, so this one is just considered 1 over 2. So root 2, which is greater than 1, 3 is greater than 2. If you try to divide it, would that be smaller? So root 2, that's about 1 point something, divided by 3. Yeah, it's going to be smaller. 1 over 2, that's going to be 1 half. So for this series, it's actually considered conditionally converges. Okay? So try to use the ratio test. We'll see that the limit is 1, so it's inconclusive. But we try to use the alternating series, so the series itself actually converges. So therefore the series converges conditionally. Well, because that's the absolute convergent, we don't know what that is. It's inconclusive. So we just want to verify that the alternating series. Okay, so thank you for watching the video today. So I'll see you guys next time. Have a great one.